My dear students, this is the last topic of your syllabus of fabric manufacturing 3D weaving, three-dimensional weaving. So in this particular session, we shall discuss about very basics of 3D weaving. So session outcomes of these sessions are, you will be able to define 3D weaving, describe principles of 3D weaving, and classify 3D weaving. Three-dimensional fabric structure. Fabrics in two-dimensional or 2D sheet form have many properties such as being drapable, flexible, warm, and strong. That you know, whatever we have discussed till date, that is on 2D weaving, two-dimensional weaving, where weft and warp, a set of weft and set of warp are interlaced together to form a two-dimensional sheet-like form that is called 2D fabric. But now in this chapter we shall discuss about three-dimensional fabric. We shall add another dimension in the fabric in the thickness direction. So making structure that have substantial dimension in the thickness direction formed by layer of fabrics or yarn. So we shall actually increase here the thickness dimension by addition of extra layer of fabrics or yarn, generally termed as three-dimensional fabrics. So three-dimensional fabrics are having the improvement in the thickness direction, and which is by the addition of extra layers of fabrics or yarns. The immediate advantage of fabrics with a notable thickness direction include the structural integrity of the woven structure. If we will improve the notable dimension in the thickness direction, then it is possible to obtain a structural integrity of the woven structure. We can stitch the fabric or yarn by applying them by the sewing operation, but then the structural integrity cannot be achieved because the stitching points will be the weaker than that of the main layers or plies. But if you interlace the yarns and fabric directly with the base layer, you can form a integral weave structure or woven structure that is called 3D woven structure. The satisfaction of geometric shape, volume required by many end-use applications. So this kind of integrated 3D woven structure satisfies geometrical shape and volume required for many end-use applications, such as most of the important applications in the structural composites, textile structural composites. Okay, in structural composite, the skeleton or the reinforcement part is actually served by this kind of 3D woven structure. The new weaving technologies arrange warp yarn in 3D shape and allow weft yarn to be inserted at different levels in one or two directions. So this is the basic principle of 3D weaving, where the warp yarns, they are actually organized in a three-dimensional shape, and weft yarns are made interlace or insert in between those warp sheets which are coming from the different direction to make an integrated 3D woven structure. Now come to the principle of making 3D woven structure. The conventional 2D weaving process using three sets of yarn, ground warp, pile warp, and pile web. That is, you already studied in your terry pile class to produce pile fabric. So for the production of the pile fabric, one ground warp beam is required, one pile warp beam is required, and weft is required for the insertion. The pile warp, which are actually creating the extra thickness in the thickness direction. So that's why this is also, you can say, one type of three-dimensional structure, but that is not the truly 3D woven structure, because pile loops are very loose in nature. That's why they are called 2.5D fabric. Okay, that is not exactly or truly 3D fabrics. The conventional 2D weaving process is designed to interlace two orthogonal sets of yarn. Two orthogonal sets means the warp and weft sets. with an additional set of yarn. If you use additional set of yarn other than the warp and weft as a binder warp or interlacer yarn through the thickness or z direction, this is referred to as multi-layer weaving and produces an interlaced 3D fabric constituting two sets of yarn on 2D weaving device. So you can understand, okay, in conventional 2D weaving process there is only one set of warp and another set of weft, but in 3D principle basically there is required another additional set of yarn as a binder warp, okay, or interlacer that will interlace between those warp and weft sheets and to produce an integrated 3D structure, three-dimensional structure. So minimum 3 sets of yarns are required for production of three-dimensional fabric. The 3D weaving process is designed to interlace 3 orthogonal sets of yarn. So here, as there are 3 sets of yarn, so 3 sets of yarn to be fed into the weaving point in orthogonally, x-axis, y-axis and z-axis. The weaving set operates both row-wise and column-wise. The set formation will be in both direction, in row-wise direction and in column-wise direction. In the conventional 2D weaving process, the set formation only occurs in row-wise direction, but here in 3D weaving process, the column-wise direction, in the vertical direction also, set formation is required. This produces a fully interlaced 3D fabric when all 3 sets of orthogonal yarn interlace on a specially designed 3D weaving machines. So for that particular purpose of formation of set formation in both row-wise and column-wise and the feeding of the interlacer warp yarn, a specially designated 3D weaving machine is required. So these are the various 3D weave architectures or simply the 3D woven fabrics which are developed and present in the market. The name of the structure, their architecture and shapes are given here in this table. The name of the structure is a solid structure. Solid means the fabric body is solid. The examples of the 3D woven fabrics are multi-layer 3D woven fabric, orthogonal 3D woven fabric, angle interlock 3D woven fabric, and their shape are compound architecture with regular or tapered geometry. They have their shape in compound structure, okay, with regular and tapered geometry. Now next structure is hollow structure, where there will be the hollow like pipe-like structure will be there, or cylindrical structure will be there, which the name of the architecture is multi-layer woven fabric. The shape is uneven surfaces, even surfaces. Okay, their surface may be either even or uneven, and tunnels on different levels in multi-direction. There will be tunnels, and tunnel will be not just a single tunnel. There will be the branch tunnel. I shall show you the photographs later. Then cell structure, cell-like structure, that means a spherical structure, either single layer or multi-layer cell structure. 3D woven fabric will be there. There are spherical cells and open box cells. Okay, either there is a spherical sphere-like or hemisphere like open box cells. Then nodal structure. Nodal is actually the branched structure like a branch of a tree. Nodal structure, multi-layer, orthogonal, angle interlock. These are the 3 types of nodal structure available: multi-layer woven fabric, orthogonal, and angle interlock woven fabric. So multi-layer nodal structure also can be produced by this type of architectures. So tubular nodes and solid nodes. So nodes will be there either in the form of tube or solid. Now 3D woven fabric production. 3D woven fabric can be manufactured both with 2D and 3D weaving systems. Okay, in 2D weaving system, that is in the conventional weaving system, also 3D woven fabric can be manufactured by doing certain modification. And obviously there are 3D weaving machines where 3D woven structures can be produced. With 2D weaving, pleated or fleece fabric, terry fabric, velvet fabric, and multi-layer woven fabric can be manufactured. So in the 2D weaving machines or conventional weaving machine, after certain modification, you can produce pleated or fleece fabric, terry fabric you know, velvet fabric, velvet fabrics is also one kind of 2.5 dimensional fabric, and multi-layer woven fabric can be produced. But orthogonal 3D weave structure, fully interlaced 3D weave structure can be manufactured only by using specially designated 3D weaving machines. Okay, or they are also called specially designed 3D weaving machines. So specially designed 3D weaving machines are required for weaving orthogonal 3D weave structure or 3D angle interlock structures. Now, what is orthogonal oven architecture? How the fabric will look like? You can see these two diagrams A and B, where the orthogonal oven architecture has been shown. You can identify there are three colors of the weft. In the first figure A, red, blue, and this brown one. The thickness of the orthogonal structure is indicated by the number of layers of the warp or weft yarn. So thickness of the fabric can be either decided by number of warp present or number of weft present in the structure. Here the blue color threads are actually the warp thread. So the number of layers you can see here 1, 2, 3, 4 layers are shown here. So this is the thickness of the structure. There are two ways of orthogonal structure can be bound. The orthogonal structure can be bound or actually integrated by two ways. The orthogonal structure that use one set of through the thickness warp to bind the structure together are called ordinary orthogonal structure. This is the type A where the one set of through the thickness warp is here to bind the structure. Okay, if there is only one set of through the thickness warp used for binding the structure, then it is called ordinary orthogonal structure. Okay, so here you can see the binder yarn is only the red one. So the red one is only the single binder yarn, single set of binder yarn which is actually integrated this structure. And where the two sets of opposite traveling binding warp yarns are known as enhanced orthogonal structure, which is having a high density. Here you can see in the next figure, figure B, the red and green, there are two sets of orthogonal binder warp yarns. They are actually run in opposite direction to integrate the structure to bind the structure to form the 3D orthogonal 3D oven architecture. So here there are two types of orthogonal oven architecture. You can see the difference of ordinary 2D structure. Okay, here you can see there are minimum three sets of yarns are required to form such kind of 3D oven structure of sufficient thickness. Through the thickness yarn travel vertically between any two weft yarn layers. So the binder yarn which are actually binding through the thickness, they at least they should bind the two layers of weft yarn. The most common situation in where they travel between the top and bottom weft yarn, where you can see in this particular cross-sectional diagram figure A, where this red yarn that is actually bind the full thickness. Okay, the most common situation is this when they travel between the top and bottom weft yarn layers. Okay, these green color circles, they are the weft yarns, and the red yarn they actually bind through the thickness. Okay, this is the most common type. When the through the thickness yarn interlink with the weft yarn layers at any other level, either tapered or figured solid preforms can be created. Either tapered or figured 3D fabric can be created. Okay, here at B you can see this through the thickness binding is there for the three weft yarn layers. After that there will be the four weft layers are actually bound by the through the thickness interlaced yarn. So again after consecutive four layers of binding, then again three layers of binding will be there. So there will be a variability. So this kind of structure or architecture is called figure structure for preparation of various figures. Okay, various structure on the surface of the fabric, this type of uh, tapered structure can be produced. This is called tapered structure. Okay, whereas if the tapering will be much variable or uneven for production of any kind of figure, such as any emboss or design on the surface of the fabric, so that is called figured structure. Okay, so figured shape. So C is a figured shape. So A is the regular shape where the binding will be even. B will be the tapered shape when there will be the uneven binding in a certain level, and when there will be the rigorous uh, variation of the binding level for the formation of some figure on the surface of the fabric, then that is called figure shape. Angle interlock oven architecture. This is a different type of interlock ovens, 3D oven structure, that is called angle interlock. Okay, angle interlock structure contain a set of straight weft yarns and a set of warp yarns that weave with the weft in a diagonal direction in the thickness. Okay, here you can see this blue thread that is actually runs diagonally. That is binding the set of weft layers in diagonal direction. Okay, that's why the interlocking is in angular direction. That's why it is called angle interlock structure. The cross-sectional view of an angle interlock fabric along with the warp direction is shown here with the 7 layers of weft yarn. This green color yarns are weft yarn. There are 7 layers of weft yarns. A top to bottom binding. Here the figure A is showing the top to bottom binding. That means if you follow one blue binder yarn, that will goes to the top and then again goes to the come back to the bottom. So top to bottom binding is here. But binding to fifth layer in part B, you can see successive 5 layer is bound by this yarn. Okay, binding by fifth layer. So each and every binding yarn, they actually binding the fifth layer only. Then see the warp weighted fabric. Okay, with the A part, there is a modification in the C part where the red color threads are actually inserted across the length for weighting effect or for making the fabric much heavier and stronger. That is called warp weighted fabric. Extra set of warp is used for increasing the weight and strength of the fabric. That is called warp weighted fabric. So these are the 3 types of angular interlock oven architecture. It has been reported that the angle interlock fabric have low shear rigidity. This is the spectacular advantage of this angle interlock structure, low shear rigidity. What will be the advantage of its lower shear rigidity? The lower shear rigidity has led to good moldability. Helmets, female body armor, preparation of helmets or female body armor. This angular or angle interlock 3D oven structure is useful for making composites. Okay, because this can be molded easily, this can be folded easily at any shape. Okay, and even the structure is integrated structure and is much strong in nature. So that's why for making the composites for helmet and body armor, so this kind of angle interlock structure is very useful. When welding warp yarns are incorporated in the structure, the tensile modulus and strength in the warp direction are sharply increased. If you insert the extra warp thread in the lengthwise direction as shown here in these red lines, red threads, the tensile strength and modulus in the warpwise direction will be enhanced drastically depending upon the strength of that welded threads. So these are the advantages of the angle interlock oven architecture. Then multi-layer oven architecture. The third type of 3D oven fabric is multi-layer oven architecture. So distinctive feature of the multi-layer fabric is that they have clearly defined fabric layers in thickness of the fabric. Their layers can be clearly defined. You can identify 1, 2, 3, 4 layers of fabrics are there, and 4 layers of fabrics are actually interlaced within the structure to make an integrated form. all warp and weft yarns in a multi-layer fabric are creamed, but here one of the major disadvantages is that the all layers in warp and weft are creamed here. Okay, they are no the warp or weft yarns are not running straight here. Okay, whereas in other cases in angle interlock and 3D architecture, you can see there the yarn runs straight. There is no cream, but here the yarns are having cream. There is some binding of the warp yarn is actually binding around the weft yarn and vice versa, which lead to low initial modulus and a tensile loading along the warp and weft direction. This is the disadvantage or demerits of the multi-layer oven architecture, that the initial modulus is low due to the high crimp in the warp and weft state. 3D hollow oven preform. So preform is actually the oven fabric. Preform, this terminology is used in case of composite manufacturing, because these 3D hollow oven fabrics are also used for manufacturing composite as a reinforcement. So in that time they are called preform. Okay, 3D hollow oven preform can be generally divided into two types. One with flat loop and bottom surface, and the other with the uneven surface. Okay, flat surface simply and uneven surface. Hollow fabric with flat surface. So this type of hollow fabric incorporates three or more layers of the fabric, three and more layers of the fabric to make a flat hollow fabric. Okay, you can see this diagram: trapezoidal hollow on the flat surface, then triangular hollow flat surface, then rectangular hollow flat surface. So these are all fabric structure, oven fabric structure, which are having flat top and bottom surface, and in between there will be the either trapezoidal or triangular or rectangular hollow created. Those hollow spaces are much useful for insertion of the resin for the preparation of composites. The structure is self-opening when the resin is whipped into the fabric. The structure will collapse, but as soon as the resin will be whipped to the fabric, resin will be penetrated inside the fabric, the structure will be inflated automatically, and then the composite will be manufactured. The hollow fabric can be made in a single level or multiple level. Either hollow fabric can be made in single level. All these type of structures are single level structure, or if you want multi-level structure or multi-layer structure, that is also possible. That means another layer of hollow fabric can be developed on the top of this surface. Okay, in this way multiple levels can be created. Okay, in this bottom, the below figure, you can see the cross section of the hollow fabric, where the top layer, bottom layer, and how the interlacement of the yarns, they are connected between these two top and bottom layer to create the hollowness. Okay, this type of structure when will be there, that will produce a T shape. Okay, that's why it is called double I fabric or I shape. I fabric cross section and double I shaped structure. This type of structure is called I shape because it is like I. Okay, both with which is having both top and bottom layer. If no bottom layer will be there, then that is called T shape or T fabric. Hollow fabric with uneven surface. So 3D hollow fabric based on the multi-layer principle, according to which the adjacent layer of the fabric are combined and separated at arranged intervals. So here this figure is shown here when the surface of the 3D fabric is not even like the earlier one, the surface will be the uneven. Okay, there will be the multi-layer oven fabric and surface will be the uneven due to the differences in the interlacement. The combining and the separating of adjacent layer allow the entire fabric to be opened after weaving to become a 3D structure with cellular shaped cell in a cross-sectional direction. So if this type of structure will be created, then it will, when open, that will produce a cellular-like structure like this. So it has shown in figure B. The illustration of cross-section of hollow fabric with uneven surface, flattened form, this is the flat form, and open form in shell-like structure. So hollow fabric with uneven surface will produce cells, some cells, like shown here in this figure. 3D shell oven fabric. This is a different type of fabric. Okay, 3D shell oven fabric from doubly curved cell structure that maintain fiber continuity. In 3D cell woven fabric, the yarn or the fiber which is making those structures have a certain level of continuity. There will be no cutting or stitching of the yarn and fibers. Such fabrics may assume spherical shapes and cubic shapes. So spherical shapes and cubic shapes are produced by using this type of architecture. Such cell-shaped fabric can be made using different techniques such as weaving with discrete take-up, weaving combination, molding, and origami method. There are various methods. I shall not go in detail all these methods. You can just remember the names of these methods. Weaving with discrete take-up, profile take-up roller to take up the fabric, or the creation of the dome shape. So the discrete take-up is utilized to create a dome shape. Okay, for making the shell appearance. Use of combined weave, change in float length and yarn tension. Okay, if you can change the float length of the fabric, float length of the yarn and the yarn tension, then you can produce honeycomb weave, combination of short float weave, typically the plain weave and long float weave. So honeycomb weave also can be produced by combination of short float and long float weave. So all those techniques are used for preparation of shell woven fabric. Okay, now come to the next another type of architecture, that is called 3D nodal fabric. Okay, nodes will be there or branch will be there. The term 3D nodal fabric refers to fabrics that facilitates network formed by the different tubular or solid members joining together. Okay, you can see how the network can be created by joining different members. Okay, woven flanges are required to have an area for defining and joining the two cloths together by stitching to obtain the tubular structure. So these are the called flange. This flange part is required for stitching and joining two parts, the bottom and top part, to create this kind of nodes or nodal structure. So these are the 3D nodal structure. They are also one type of 3D woven architecture. So now 3D woven architecture can be formed specially made devices, or which are called specially designed weaving machines, okay, or weaving technologies. So basically most common technologies are non-interlacing weaving device and the 3-tex weaving principle. These two principles are available. Non-interlacing weaving device. Here you can see the two sets of warps are coming at a point, and from the top there will be another set of threads will be coming, and all those will interlace here at this position to prepare a 3D woven structure or 3D woven architecture. Or in the 3-tex weaving principle, where 1, 2, 3, 4, 5, 6 weft yarns are inserted simultaneously, and the binder yarn, that the red color yarn, that will actually bind all those yarn together before the bit up operation. So in this way, this type of 3D woven architecture can be produced by the 3-tex weaving principle. So this is an example of uniaxial 3D woven fabric and the modified conventional weaving loom. You know, in the conventional loom there will be the single warp yarn and single set of weft yarn. But here the set will be produced as many. Okay, many sets will be produced and many wefts will be inserted in each and every sets. You can see 1, 2, 3, 4, 5 sets are produced here, and 5 yarns are actually inserted, and after that the binder yarn will wrap over all the inserted weft yarn. Okay, then the bit up will be done to create this kind of 3D woven fabric, which is shown in figure A. Okay, so this type of some modification is required in the existing 2D weaving machine to insert this binder yarn to bind the all inserted weft yarn. This figure, the similar figure already I show you. Okay, where two sets of warp sets are coming, and from the top there will be another sets of binder yarn will coming, and they both will interlaced here at this position orthogonally to create the multi-axial 3D fabric architecture. So this is the typical 3D architecture where you can see all the yarns which are forming the fabric have no cream. All the yarns are unstraight, but they will interlace to lock the structure to form an integrated woven architecture. So this type of structure is actually the true 3D woven structure. So here the multi-axial 3D orthogonal woven fabric structure is shown. Okay, here also you can see how the fabrics are interlaced, how there are bias yarn, warp yarn, weft yarns, and again there is a second set of bias yarn. Okay, so this is the unit cell has been shown, unit cell width and unit cell thickness is also shown. So in this way, the woven architecture of the 3D woven fabric can be represented. So that's all for the 3D weaving in brief. I hope this topic is interesting to you. Okay, and this is the end of your syllabus. Whatever I taught you, you should revise them all and prepare yourself for the final examination. Best of luck.